Hi, I'm Marcella Billick. Welcome to my second lecture, Technology and Solutions. Let's quickly recap the last lecture entitled Consensus in the Science of Climate Change. We examined the aspects of science that make it reliable and predictive. We explored the reasons why controversy in science is very unusual and noted that scientists agree strongly that climate change is occurring as a result of greenhouse gas emissions caused by human activities. So climate change is real and needs our urgent attention. In this lecture, we will try to figure out how much time we have to act and what tools we have available. Modeling the long-term effects of climate change is difficult because the planetary, ocean, and atmospheric systems that drive our climate are complex, with many feedback loops. The models clearly show that warming is happening due to the accumulation of greenhouse gases, but there are uncertainties as to exactly how much warming will result from a given future release of greenhouse gases. We know for sure that we have only a finite amount of CO2 to emit before we condemn large parts of our planet to becoming uninhabitable. This is known as the remaining carbon budget. To mitigate the damage, we must limit the total amount of warming since pre-industrial times to less than 2 degrees, or for better outcomes, less than 1.5 degrees. Climate models can be used to determine the remaining carbon budget consistent with these limits. But because of the uncertainties, there is a distribution of answers, each with a given probability of being correct. This can be viewed as a probability distribution as shown in the diagram, where the height of the curve at each point indicates the likelihood of the value on the horizontal axis being the remaining carbon budget. The probability that we can stay below 1.5 degrees global warming is 2 in 3 if we can limit all future emissions to 230 billion tonnes, the blue line, because 2/3 of the predicted budgets lie above that. If instead we limit future emissions to 440 billion tonnes, the red line, the probability of keeping the warming below 1.5 degrees drops to 1 in 2, as only half of the predicted budgets lie above it. There is a 1 in 6 probability, which is the fraction of budgets in the grey area, that we have already emitted too much CO2 to keep the average temperature rise below 1.5 degrees. To get an appreciation of what these carbon budgets mean in terms of speed with which we need to cut emissions, if we target 230 billion tonnes, we need to linearly decrease global emissions from 2019 levels to zero by 2032. That is, we have about a decade to cut back to zero greenhouse gas emissions. Whilst to have a 1 in 2 chance, like getting heads on a coin toss, we need to reduce emissions linearly to achieve net zero by 2042. That is, in only 2 decades. And there is not an insignificant chance that we have already missed out on a 1.5 degrees target. Just to give you a feel for how big the cuts required are, we need to achieve the same level of reduction which occurred due to COVID lockdowns, about 7%, every year for the foreseeable future. This is not an easy task, and we need to target investment to systems and technologies that most aggressively achieve emissions reductions, starting now, to give us the best chance of success. Here is a graphical representation showing the rates of decarbonisation needed to limit global warming to an average temperature increase of 1.5 degrees, taken from the Intergovernmental Panel on Climate Change 1.5 degrees report. Very sharp cuts are needed over the next 10 years to enable us to not exceed a 1.5 degrees average temperature increase. The slower our rate of reduction this decade, the more the trajectories move into negative emissions. And negative numbers mean that we will need to be taking carbon dioxide out of the atmosphere and storing it, so that the amount we capture and store exceeds the amount we release that year by that negative number across the entire planet. We need to make it to zero net emissions by 2050. To tackle this problem, we first need to be aware of what is causing it. Energy from burning fossil fuels in all its forms, such as coal, oil, petrol, diesel, and gas, is the highest source of CO2 emissions. The red piece of the pie in the circle representing global emission sources in 2020, and all except for the grey rectangle in the slab on the left representing Australia's emissions from 2015. In both cases, emissions from energy generation and energy use is responsible for almost 3/4 of CO2 emissions. About a third of that is energy used in industry, mostly to manufacture materials and products that we buy. Of the remainder, about a third is used in transport and another third in buildings, both residential and commercial, for purposes like lighting and climate control. The last third is largely unallocated, and almost a half of it is fugitive emissions from energy production, almost 6% of the total global CO2 emissions. These arise from leaks in gas lines, spillages, and so on, and do not even result in useful energy. Clearly, the most important thing we must do is stop using fossil fuels to produce energy. This alone would bring massive reductions, cutting our emissions by about a factor of 4. The grey pie is associated with CO2 emitted in chemical reactions performed to make products and materials such as cement, while the blue and green pies correspond to emissions from waste incineration or decomposition in landfill and emissions from agriculture and deforestation. About a quarter of the green pie is attributable to livestock, so cutting back on meat consumption in our diets would also have a significant impact on tackling climate change. Okay, so given that direct energy use is responsible for the biggest by far portion of emissions, let's explore what can be done to reduce that to zero first. Switching our energy production from fossil fuels to renewables is a no-brainer. As shown by the data from Our World in Data, renewables are much safer, provide more and better jobs, and produce only small amounts of emissions which occur in fabrication of the infrastructure and not in use for energy production thereafter. Renewables are already cost-effective, with solar and onshore wind delivering energy at lower costs than all fossil fuels. Additionally, the price of the energy they produce has plummeted over the last decade and is becoming still cheaper, with the trend set to continue. Some of the early technology underpinning solar was developed in Australian universities, but lacking investment here was picked up overseas, and now we buy it in the form of solar panels. Given the dramatic growth that this industry has seen, I think it's too bad that Australian investors let it go. I would be surprised if the alternatives that they invested in performed as well. Since these highly competitive renewables make electricity, we should try to electrify as many of the greenhouse gas emitting activities as possible across all of the direct energy sector. This is pretty straightforward in most industrial applications and in buildings, but harder in transport. Shifting to electric vehicles for road and rail transport for short journeys is already feasible and close to being cost competitive with fossil fuels. As the prices of electricity from renewables continues to fall and charging infrastructure increases, it will also become the most economical choice. Long-haul trucking, shipping, and aviation are more difficult due to the weight and size of the batteries that would be required. So what has made the production of electricity using solar energy and wind so cheap that it is now favoured by market forces? Rapid cost reductions of infrastructure, construction, and efficiency gains of electricity production from solar panels and wind turbines over the last few decades have led them to become cost competitive with well-established fossil fuel technologies. Let's try to understand why these rapid reductions in costs occurred, so that we can emulate this process for technologies that can eliminate emissions in harder to abate areas, but are still too expensive to be brought to bear by market forces alone. Solar and wind have become so cheap due to the learning that comes from increased production. The more manufacturers of solar energy infrastructure produced, the more they learned, enabling them to refine their production processes and invest in R&D, finding ways to make their products more efficient. The resulting lower costs and better performance further increased demand for solar cells, so they could produce and sell bigger volumes still, perpetuating this virtuous cycle. Every doubling in the number of solar cells sold and deployed brought a 20.2% reduction in their cost of fabrication. Since they were also more efficient in producing electricity, the cost of the electricity from solar cells fell at an even faster rate, with a 36% reduction for each doubling in capacity deployed. Although there is initial outlay to build and install the infrastructure for solar and wind, this is now similar to the cost of new fossil fuel power plants, and the running costs are much lower because the sun and wind are free, whilst fossil fuels must be regularly purchased. This is making solar power plants more profitable than fossil fuel power plants, so energy sector investors are shifting to renewable systems. Learning curves such as these are observed for many technologies. In the case of microelectronics, this learning curve is known as Moore's law. The good news is that batteries have similar learning curves. The faster we can grow the markets for them, the sooner they will become price competitive against liquid fossil fuels for energy storage. The learning curves have made electrification powered by renewables feasible and inexpensive over much of the energy sector. We need to move as quickly as possible down this path and replace all fossil fuels used for the generation of electricity by renewables as soon as possible. By doing so, we will further accelerate the learning curves and end up with still cheaper energy that just keeps getting cheaper. So rapid decarbonisation of power can be achieved with existing technology now. And by doing so, we will reap future reductions in energy costs as we propel the learning curves further. In practice, this means phasing out all fossil fuel electricity generation plants and replacing them with renewable energy generation capacity. This should be done in tandem with gradual electrification of as much of the economy as possible, mainly light-duty road transport, manufacturing, and residential cooking, heating, and cooling. This means converting everything we can that currently runs on oil, petrol, or gas to run using renewable electricity by means of energy storage using rechargeable batteries. Examples include lawnmowers, cars, buses, cooking, hot water. This strategy is detailed in the Energy Transition Commission's report entitled Better Energy, Greater Prosperity, published in April 2017, which demonstrates that the dramatic reductions in the cost of renewable electricity generation and of energy storage options make it possible to plan for cost-competitive power systems which are entirely dependent on renewables. In the transition process, it is important to ensure that the pace of electrification is adapted to match the pace of power decarbonisation so that we avoid using electricity generated from fossil fuels to charge batteries used to run electrified vehicles and appliances. Today's battery technology does not have sufficiently high energy density, that is energy per unit of weight and volume, to make current batteries capable of powering long-haul trucks, ships, and aeroplanes. The energy needed to make a journey of thousands of kilometres would require a prohibitively big and heavy battery. In addition to long-haul transport, heavy industry, such as the production of cement, steel, aluminium, and plastic, cannot be brought to zero emissions using renewable energy sources and batteries alone. Unfortunately, the chemical reactions used to create these materials themselves produce carbon dioxide as a byproduct. Together, these and long-haul transport are termed the hard-to-abate sectors. A plan detailing how to bring emissions to net zero in these sectors is put forward in a 2020 report entitled Making Mission Possible and published by the Energy Transition Commission. The ETC, or Energy Transitions Commission, is an international think tank established in London in 2015, consisting of 32 commissioners, including individual experts, company and government leaders. It develops roadmaps to meet the twin objectives of economic development and climate change mitigation. Making Mission Possible explains how we can attain net zero emissions in all of these sectors for a cost of less than 0.5% of GDP. Long-haul transport would use renewable fuels, such as hydrogen, ammonia, and biofuels synthesized using electricity from renewable sources, while the CO2 byproducts from the production of building materials could be captured as they are being emitted and stored to prevent them from entering the atmosphere. To keep the cost below 0.5% of GDP, the strategy detailed for the manufacture of materials in heavy industry relies on increased recycling of plastics, steel, aluminium, and cement, driven by strong policy incentives. This measure would dramatically decrease demand for the production of new materials. When making new materials, electricity generated using renewables would be used instead of fossil fuels to heat the furnaces and kilns used in the production processes. Alternatively, hydrogen or biomass could be used for generating heat for kilns and furnaces, and these same fuels could be used to decarbonize the chemical reduction reactions required in the processes. Biomass could be used to substitute fossil fuels as the feedstock for carbon in plastics. Any carbon dioxide produced would need to be captured at the site of production and stored, ideally in a solid form, and prevented from reaching the atmosphere. Similarly, reduction in demand for heavy emissions long-haul trips through more efficient logistics and shifting some transport to lower emissions modalities is the first step in the strategy to reduce emissions from long-haul transport. Gains from energy efficiency are expected to further reduce the total energy needed. Electric drivetrains with battery or hydrogen energy storage have efficiency advantages over internal combustion engines and are projected to become cost competitive with diesel or gasoline in the 2020s. This would bring long-haul road transport to net zero emission if the batteries are charged and the hydrogen produced using electricity from renewable sources. Short distance shipping and aviation could also be powered by batteries or hydrogen from renewable sources. But long-haul aviation and shipping would use bio or synthetic jet fuels and ammonia or biodiesel respectively. Again, these fuels must be created using electric power from renewable sources to enable these strategies to deliver net zero emissions. The strategies laid out in the ETC Making Mission Possible report are capable of delivering net zero emissions in hard to abate sectors now. However, unlike switching our electricity grids to power from renewable sources, these strategies cannot currently compete on price with fossil fuel alternatives. As noted in the report, there will be excess costs that we need to cover if we choose to zero out emissions from these sectors. In his new book, published in February of 2020 and entitled How to Avoid a Climate Disaster, Bill Gates terms these excess costs green premiums, defined as the difference in cost between doing something in a way that produces greenhouse gases and doing the same thing without greenhouse gas emissions. He argues that although paying these premiums is a cost now, it presents an excellent investment because not only will we mitigate a lot of costly future climate change damage, but we will also send these technologies on rapid learning curves that will make the solutions cost competitive and eventually even cheaper than the mature fossil fuel technologies whose costs are tied to fossil fuel prices and unlikely to decrease. It really seems like a no-brainer that we should find ways to pay the green premiums in the short term to reap significant long-term benefits. We should target investment and R&D funding to activities with high green premiums to accelerate the learning curve cost reductions there. More R&D allocated to clean technologies is highly appropriate because it is currently a tiny fraction of the amount spent on R&D in medicine, whilst the annual death toll associated with fossil fuel emissions is greater than that due to COVID-19 in 2020. We should put a price on carbon emissions to reflect the damage they cause and use the funds to incentivize investment in emerging clean energy alternatives to accelerate learning curves where green premiums are still high. Because these actions will not yet be incentivized by markets, we need governments to create the necessary incentives and stability for investors. Some politicians in Australia have noted that our abundant renewable resources suggest that investing in green technologies to develop zero-emission manufacturing, particularly for the processing of the ores we export, would position us for strong economic growth. Not only could we license the clean technologies we develop and refine through learning curves, but we could tap strong international markets for our products as other countries try to eliminate emissions in their supply chains. I will finish here with two images from the ETC Making Mission Possible report. On the left, we have a pictorial representation of all of the solutions we currently have in hand to make it to zero emissions. It is really important to realize that it is all there, although some of the technologies are emerging and still more expensive than fossil fuel alternatives. Don't forget, though, that solar energy was in that place not so long ago. All we need to do is grow the markets using other incentives for a while, and the learning curves will reduce the costs so that we will be better off, both in terms of costs and environmental impacts in the long run. However, as shown on the right, it will take concerted cooperation from many sections of our economy to make it happen. The importance of government policy is evident, as policymakers are necessary to move forward on 9 out of the 10 objectives identified in the Making Mission Possible report, while innovators appear in only one objective, reflecting the fact that the technologies we need are already developed and available. In our next lecture, we will talk about what is currently being done and why is it that we are still moving so slowly. We will explore which stakeholders are taking useful action and why. Who is failing to do their part and why? What is the role of the general public, special interest groups, and the media in how this plays out. Thanks for watching, and I look forward to seeing you again for my third and last lecture.